Welcome to Chapter 16's first lecture. This will follow along in Chapter 16.1 and 16.2. We'll be looking at introducing waves, different types of waves, both longitudinal and transverse, and the parts of a wave. A wave is any disturbance that carries energy from place to place. There are all types of different waves that we'll look at. There are mechanical waves, which move a substance. They move a material. It's a disturbance in a material. That could be like a water wave, a sound wave, are all mechanical waves. They involve the motion of just like molecules and matter in general. Then there's electromagnetic waves, which we'll look at a little bit later on, which they do still carry energy, but in a different form. It's a changing magnetic and electric field. But a wave is just a disturbance that carries energy from one place to another. There are two types of waves. The first type of wave that we'll look at is a transverse wave. In this case, the disturbance is perpendicular to the direction of travel for the wave. So here we have the wave itself traveling down the slinky from left to right. The disturbance is moving up and down. So the disturbance is moving back and forth in a direction that is perpendicular to the motion of the wave. Electromagnetic waves are transverse waves. We'll also see these whenever you move back and forth like a string or something else there. So we'll see those often in class. The second type of wave that we'll look at is a longitudinal wave. In this case, the disturbance moves in a direction parallel to the motion of the wave. So here we have in the slinky is, as you can see, the compressed area moves in an area in the same direction that the waves moves on. And what we'll have is we have an area of compression and an area of what's called rarefaction, where the spring or whatever the matter is stretched out. Longitudinal waves only occur, they're only mechanical waves, so they only occur within matter. The most common example is sound wave. Sound is a longitudinal wave. Not all waves are necessarily classified within transverse or longitudinal. You can have combinations of both of them. For example, a water wave actually has both a transverse and longitudinal component to it. So a water molecule will move up and down and kind of actually ends up moving in a circular motion. The direction of travel for the wave continues on, in this case, from left to right from our drawing, but they're not necessarily just a straight-up transverse or longitudinal, but rather a combination of both of them. All right, parts of a different wave. So periodic waves are any waves that are repeated over and over again at a constant rate. There are a couple parts. There's one, the top part of a wave, the little bubble is called the crest, the top ridge is called the crest. Where it crosses the equilibrium point, that's called the equilibrium point, it crosses zero kind of for the y-axis, that would be the equilibrium point. And when it gets to the bottom, that's the trough, T-R-O-U-G-H. So the bottom part is the trough. The wavelength is the length for one cycle. Similarly, the period is the time for one cycle. Wavelength is always measured in meters. And that can be from a crest to a crest, a trough to a trough, but it's any full complete cycle, so one back and forth motion. Amplitude is the distance from equilibrium to the maximum, either the crest or the trough. So it's the maximum displacement from equilibrium. Once again, period is the time it takes to complete one cycle, or it's the time it takes for one wavelength to go by. Period is the inverse of frequency. So frequency is how many cycles per second, or frequency is equal to 1 over the period. So it's the rate that a wave is oscillating, the rate at which it moves back and forth. So period and frequency are related, And period, once again, is the time it takes to complete one full cycle or wavelength. Speed is measured in length per time, units of length per time, so that's meters per second. The wavelength is obviously wavelength is a length, and time is usually measured by the period, the time for one cycle. So wavelength over time will give us wave speed, but we can also rewrite this to say that 1 over the period is the same thing as frequency. So we could say that wave speed is the frequency multiplied by the wavelength. So frequency is units of 1 over the seconds, wavelength is meters, wave speed, frequency times wavelength, meters per second. All right, 2 easy questions and one that involves probably a little bit more thinking. So first, what is the difference between longitudinal and transverse waves? Second, what is the difference between mechanical and electromagnetic waves? Both of those things were touched on in the video earlier, or I'm sure they're in the textbook. Mr. Wolf, this third question, loves 2 different radio stations. 102.5 FM, this is a country radio station. It's broadcast in megahertz. That means a million of hertz, which is the unit of frequency. So that's 102.5 MHz, megahertz. And he loves 8:50 AM WEI. That's where the Red Sox play on there. And that's broadcast in kilohertz. So 850 kilohertz. Kilohertz is 1,000 hertz. Given that all radio signals are electromagnetic waves that travel at the speed of light, 3 times 10 to the 8th meters per second, what are the respective wavelengths for the 2 different radio stations? So a little bit of a plug and solve right there. Make sure to pay attention to scientific notation there. Thank you very much. Have a good night, and I'll see you in class tomorrow.